So in this video, I'm going to talk about Bronsted-Lowry acid and bases and how we figure those out. But I'm going to start off with a little review of what we know about acids and bases so far. If you already know the basics on this, you can skip right down to the Bronsted-Lowry stuff, okay? And included in this video is going to be some of the items that you may have seen in your homework that we haven't yet gone over in class. So let's review all those. Okay, so an acid is a solution with hydrogen ions in them, okay, which we call H+ ions, right? So hydrogen that has lost its electron, so it's just a little proton, okay? So H+ is the same thing exactly as one single itty-bitty little proton, all right? And in Arrhenius's world, we said we can always know what's an acid because they always start with the letter H in their formula. Okay. Similarly, a base is an aqueous solution that has hydroxide ions in it. And we would always see the hydroxide ions. The hydroxide ions would always have a negative charge associated with them. And in Arrhenius's world, we always had the hydroxide in the formula for that particular base. And when we looked at what bases were, we said, okay, here I've got hydrochloric acid. It's aqueous. In other words, it's in water. Here's my water sloshing around. And what you can see is the little hydrogen ions have all dissociated from the chlorine ions. So they're completely dissociated. And that is what makes hydrochloric acid a strong acid, is this dissociation from each other. And because it's a strong acid with all this dissociation, it's also a very strong electrolyte, which means it can carry electricity very, very well because all these little charged ions can line up together to carry an electrical current. Okay. Conversely, over here we have hydrofluoric acid. So again, it's in an aqueous solution, a solution of water. But when we look at it, what we see is a lot of my little compound has not dissociated. It's still together even here because this fluorine ion is just so extremely electronegative. It's very selfish. It will not let go of that hydrogen for anything in the world. So very little of it will dissociate. Because of that, it's considered a weak acid. And because it doesn't have many ions available to line up to carry that charge, it's considered a very weak electrolyte as well. Okay, so that's the world of acids. And we see something quite similar go on with bases. So over here in our sodium hydroxide in an aqueous solution, what we see is, strong. Okay, so what we see with sodium hydroxide is it's completely dissociating, isn't it? Right, and therefore it's considered a strong base. Okay, and therefore it's considered a strong electrolyte. Same reasons exactly. It's ionizing and therefore it's strong. Okay, conversely over here we've got a weak base. So what is this? This is ammonia that is in an aqueous solution, a water-based solution. And look what's happening. These ammonia compounds are sticking together pretty much. There's only a slight bit of ionization going on. And because of that, it's a weak base. And because of that, you guessed it, it's a very weak electrolyte. It just doesn't have enough ions that will get together to carry an electrical current through that solution. Okay, so now that we've got these basic definitions, and again, we're talking Arrhenius acid definitions here with our H and our OH, we can say, okay, so how do we measure these things? Well, what we do is we use pH, and you know the basics of pH, right? That what pH represents is a concentration of hydrogen ions that are in a solution. However, what we have just learned is that this number here, the pH number, is the negative log of the concentration levels. And what that means is the log of the concentration levels mean it's 10 to the what power. And so that's where our number comes from. And it's a negative log because here we have -3. And what that means is that if we were to document this out, not in scientific notation, we would say 1/1000th or 10 to the -3. So that 3 represents that we've got to have that in the third decimal point to the right of our decimal point, right? So there we have it. 10 to the -3 moles per liter of hydrogen ions are present. Now, the only reason I have this line here is standardly, when I've been in any chemistry class at all, we've always represented hydrogen ions this way. However, your book shows hydrogen ions this way as H3O+, all right? So these two mean exactly the same thing. They're exactly synonymous. This is just the way the book chooses to do it. It may be more really accurate to what's going on inside of that solution, but on your test, you're probably going to see it this way, and on your homework, you're probably going to see it this way. But just know that these are the exact same things, and what they really represent is this right here, once you get out of scientific notation. Okay? The other thing to know is that when we talk about this, we're talking about two things that affect this. Number one is the concentration of solution. In other words, how much sodium hydroxide did I put into my water here? Okay, and that's molarity, like we learned about, or moles per liter, like we learned about in solutions, right? And then the other thing that affects it is strength, and strength refers to ionization. Okay, so these two things are working together, and you'll need to be able to differentiate these two terms and what they really mean. Okay, all right, so this is when we have an acid. So what happens when we have a base? Well, as you know, when our pH gets above 7, we've got a base going on, and therefore the concentration of hydrogen ions in that solution is very, very small. So again, I take this, I make it a log, and I make it a negative log, and therefore it's 10 to the -10. So here, after my decimal point, if I take it out of scientific notation, I would have 9 zeros and then my 1, and that's the concentration of hydrogen ions per mole per liter. It moles per liter, okay? The other basic fact that I want you to always remember is that you can add up pH plus pOH. They're always going to equal 14. And therefore, if I gave you either one of these, you would be able to figure out the other one. Similarly, because this is a negative log number, I know that if I multiplied my hydrogen ion concentration by my hydroxide ion concentration, I would always come up with a value of 1 times 10 to the -14. Okay, so mathematically, if I gave you any of these 4, you could intuitively deduce any of the remaining 3 items. Okay, either by just simple arithmetic or by using your calculator in ways that we've started to go through in class. Okay, so that's a little bit of background. So now let's talk about Bronsted-Lowry bases some more, okay? So when we talk about a Bronsted-Lowry base, remember that Arrhenius said every acid and every base, acids start with an H for a hydrogen ion, or maybe more than one hydrogen ions present, and then bases have that hydroxide ion. So that's what he came up with, and for the first 50 years of that theory, it stood just fine. And then Bronsted-Lowry noticed that there were particular substances that seemed to function like acids and bases, but they didn't have that H and OH in their formula the way you would expect that they would. So they looked to see and did experiments to see what was really going on with these particular things that seemed to sort of be pseudo-acids and pseudo-bases that were functioning perfectly like it without the same formula. And what they come up with was, what was going on was there were substances that were donating protons, okay? And and they said those are acting just like an acid by donated proton. So remember, acids donate, okay? And then they said the substances that were acting like bases were accepting a proton, okay? So bases accept. And I'm going to ask you to remember this concept by remembering Jesus is the answer to everything. Acids donate, like AD, right? We use AD for Anno Domini, the year of our Lord, the year of Jesus' birth, or at least the alleged year of Jesus' birth. We don't know exactly when he was born. But anyway, acids donate, okay? And therefore bases accept. So when we give you a Bronsted-Lowry problem to figure out, this is going to be the key to how you work. So what do these problems look like? Let's look at this one that we went over in class. And what we see is we've got here a particular substance, this aqueous solution, combined with water. Water we don't identify as an acid or base according to Arrhenius. But what we see here is a donation has occurred, and therefore these substances are acting like acids and bases. So let's look at what went on. What we would say is, okay, I've got a neutral substance here, a neutral substance here, that's become a plus, and this has become a minus. So the first thing we always do is we identify the charges that are present on each particular substance that we've got involved in our reaction. And next we come along and say, okay, I know that acids donate, so who donated what? And I say my neutral thing here became a positive, so it accepted. So this is a base here because it is going to be accepting a proton. Then we look over here and say acids donate. Did this guy donate? Yes. He went from neutral to negative, so he lost his positive charge. So he was an acid that donated. Okay? So I've got my base and my acid figured out. The next thing we need to know how to work these equations is we say, okay, whatever was my acid became my base. So this is my conjugate base. Whatever was my base became my acid. So this is my conjugate acid. So what happened here is my acid and base are always going to be over here in my reactants. My conjugate acids and conjugate bases are always going to be here in my products. Okay, you'll never have a conjugate anything over here. You'll never have anything that isn't a conjugate over here. All right, that's always going to be the case. And whatever was my base here is going to become my acid. Whatever is my acid here is always going to become my base. Okay, so again, the first thing we do, we look and say, what's the charge on all of my compounds that are involved in this particular reaction? Then we say, who is donating? And we know that whoever is donating is the acid. Whoever is accepting, therefore, is my base. And that's how we figure those out. So let's do a couple. Here's my steps. So first, let's label the charges. Neutral, neutral, positive, negative. Okay? Next thing we do is determine how the charges change. So my iodine goes from being neutral to being negative. So it has donated, hasn't it? Okay? And therefore, acids donate. So this is my acid donating. Okay? And anything that is an acid here becomes a conjugate base. All right? Then over here, this must be my base that is accepting. And sure enough, look at that. It goes from neutral to positive. So here's my base. And so a base over here becomes the conjugate acid over here. So there we have that. Okay, let's do this one. No charges, this is neutral. No charges, this is neutral. plus negative, okay? And therefore, this goes from neutral to positive. So it is accepting. So therefore, this is a base, because bases accept. And then this must be an acid. Acids donate. And sure enough, he donated. He gave away a hydrogen ion. So he's my acid. And therefore, he is my conjugate base when he gets over here. This guy goes from base to conjugate acid. So they always do a switcheroo. Always, always, always. All right, now this one's a little bit more tricky. So let's look at this one next. Here we've got a 2 negative for a charge. Here we've got a neutral. Here we've got a 1 negative, and we've got a negative. Negative and negative, can that be? Well, yes, it can, because I've got a 2 negative over here. Because what's happened here? Well, let's start off by what is neutral. So with neutral, I've gone from neutral and I've donated. I've lost. When you go from neutral to negative, that means I've lost 1 positive charge, and therefore I am an acid because I donated away that positive charge. So here's my acid. That makes this guy my conjugate base. Okay. Now, so this must be a base, right? I'm going to write in B, but let's see what it did. It went from 2 minus to 1 minus. Bases accept. All right. And that makes sense that he became more positive. Even though he's still overall negative, he became more positive. So he did accept this hydrogen ion on him. And therefore, he is a conjugate acid. Strangely enough, he is a conjugate acid. Okay. So there we have that. Now, let's see some more examples. So what I want you to always remember, I'm going to write it up here, is acids are donating, bases are the accepting. So AD, that's what I remember. All right, so here we're told these are acids, so we know that they are donating, and therefore they are losing an H+. And therefore this HBr, the conjugate base, is going to be Br minus. Okay? Same thing here. We've lost 1 hydrogen ion, so it's going to be ClO4 minus. Okay? H2CO3 is either going to become CO3 2 minus, or it's going to become HCO3 minus, okay? So if I lose 1 hydrogen ion, then I'm going to become this, right? If I lose both hydrogen ions, I'm going to become my little chlorate ion with a 2 negative charge. Remember learning that last semester? Yeah, okay. And now let's look at this guy. If his, as an acid, is donating, then he's going to become C2H3O2 minus. Okay? So for these bases, write the conjugate acid. We're going to write CH3NH4 plus. Okay, now how did we know that? Well, what we said was we are accepting a proton, and we know that what that means is accepting an H+, and therefore what I did was I ended up adding 1 hydrogen ion here and making a plus. Now you say, well, Mrs. Wilson, how did you know to add it there and not here? And the reason I knew that is one of the hard facts that you've got to memorize is that our ammonia ion, whoops, is ammonia, hold on just a second. Yeah, so our ammonia ion is where we would put that charge, okay? So when we add H plus, we have to add the H, and then we also have to add the plus charge unless we're reducing a negative. So for example, let's look at one of those examples. So if I am adding an H plus ion here, I would have HCl. I don't have a plus charge because I'm using my plus to negate this minus, right? Okay, and here on this one, I'm going to say, you could either say HC5H5N, I would accept that with a plus, or you could say C5H6N plus. Okay, so again, it's when it's neutral and I add my H plus, I've got to add an H, and I've also got to add a plus. Okay, F minus, so here again, hopefully you don't see this too much in chemistry, right? I'm adding an H plus, but I'm using my plus to negate my negative value that I had there. Okay, all right. Now, let's see, determine the conjugates. Okay, so for these acids, write the conjugate base. So for this one, wait, this is what we just did. Yeah, okay, so we're done with that. All right, very good.